Okay, hello everyone. In this movie clip, we are going to begin with the physics and understanding of base-width modulation. So I guess most of you are very familiar with device physics for MOSFET, metal oxide semiconductor field effect transistor MOSFET. However, you're not very familiar with physics of bipolar junction transistor or BJT. But herein, I would like to tell you the short channel effect of MOSFET from the maybe for the case of BJT. Okay, so the question is this: you know the short channel effect of MOSFET, right? As a physical dimension of channel length of MOSFET has been aggressively scaled down, the secondary effect or uh, non-ideal effects originated from very aggressively scaled down channel lengths in MOSFET has become the main issue and main technical hurdle for the device engineers to overcome in the end. So what is the core part and main topic of the short channel effect? Can you remember it? Yes, as the channel length L decreases, the threshold voltage has been decreased so that off-state leakage current has been exponentially increasing, which needs to be addressed in the end. So in the state-of-the-art integrated circuit chip, such as DRAM chip, NAND chip, or CPU, GPU, the most critical part and technical barrier should be on how to suppress the leakage or how to suppress the standby power consumption. Your smartphone is always working. Why is that? Because the transistor, which is the basic component of your application processor in your smartphone, is consuming its power. That is the main reason why your battery is out every single day. So going back to the issue in BJT, what is the corresponding or counterpart of short channel effect in BJT? Yeah, the answer is the title of this slide, base-width modulation. Okay, so since we are studying with PNP BJT transistor, and this transistor would be used maybe for analog circuit application, would be used as a amplifier so that the BJT should be under active mode. Okay, so what was the active mode? Yeah, emitter base junction. Okay, here, emitter base junction forward biased, right? What about the base collector junction? That is reverse biased, right? So going back to this cross-sectional view of this PNP BJT, and the emitter side is now common. So common emitter configuration, uh, this emitter base junction is forward biased so that the depletion layer is very small and narrow. What about the base and collector junction? Because this is reverse biased so that, relatively much wider depletion layer has been well formed compared against the depletion region between emitter and base. Then, uh, previously we talked about that maybe from here, metallurgical junction of EB emitter base junction is defined as X of 0. And here, the metallurgical junction between base and emitter is defined as X of WB. However, the quasi-neutral region, I mean, other than depletion layer, okay, the quasi-neutral region is defined as a W as a base width, and this edge is defined as at X of W, okay, from 0 to W. You remember this, and you should be very familiar with this notation. Anyhow, now the PMP BJT is hooked up as common emitter configuration, and it is working in active mode. Then the follow question is this: what is the counterpart of this configuration for or from the perspective of MOSFET. Yes, this is a P MOSFET in saturation mode. Okay, so you're very familiar with how the PMOS has been flowing its own saturation current under what biasing conditions? Yeah, source gate VSG should be positive, and the source drain VSD should be positive, and definitely the VSD should be higher than VSG minus VTH PMOS, right? So this is the biasing condition for saturation mode for PMOS. So similarly, you may see that the biasing condition V sub EB, V sub CB, common collector base junction biasing difference. Okay, think about that and counterpart of it. All right. Then now let's move on to this topic, base width modulation. The counterpart of this is short channel effect in MOSFET. So in common emitter configuration, the common emitter DC current gain, denoted as beta sub C, is defined as the input current I sub B, base current, and the output current, collector current I sub C. So this is output current, and this is input current, and emitter side is now common. Okay, so input is base, output is collector. And since this is a BJT, so input output electrical signal should be expressed with a current value. In MOSFET, the input signal should be expressed as voltage. However, the output signal for in MOSFET is drain current, right? That is current. So that is the main reason why we are talking about the transconductance stuff. Output current divided by input voltage. That should be the current divided by voltage in the unit of conductance or Siemens. So input has been transferred to the output so that we can call it transconductance. What about beta DC? Common emitter DC current gain. Yeah, input, output. Okay. All right. So in the previous lecture note, we have developed the full equation for I sub C and I sub B. You remember the very long equation, right? If not, if you forget it, please go back to the uh, corresponding lecture note to double check if you know the full equation for I sub C, collector current, as well as for base current or I sub B. So plug in those very long equation into here and there, and you're gonna end up with this. Okay. And since now the PNP has been okay, the once very well trained engineer has appropriately designed this BJT, PNP BJT, then most likely the quasi-neutral base width should be much shorter than the minority carrier diffusion lengths in base, which means holes minority carrier hole diffusion length in base, because this is an n-type, right? So the minority carrier should be whole from injected from the emitter. Okay. All right. So if this condition has been well satisfied, then the second term would be very asymptotically or very equal to 0. Okay, so you can ignore the second term. Then your beta DC value would be expressed with this equation. Okay. And one more thing is, since we are talking about the base width modulation, what if the W decreases with increasing V sub BC? I mean the base collector junction voltage here, base collector junction voltage. If V sub BC is increasing, the W should be decreased. Why is that? Base to collector junction, VBC. I'm talking not VCB, VBC, right? So this is a P-type. Collector side is P side and base side is N-type, right? So VBC is increasing, which means VCB decreasing, and VC is P side and this is N side. So in PN junction, the voltage across PN junction is decreased, which means reverse biased one, right? So base collector junction is more reverse biased. In other words, with increasing width of BC, what happened to the quasi-neutral base width? Where under reverse bias, as we have learned, this depletion layer would be expanded out, right? So that the quasi-neutral base regime should be narrowed down. I mean, this W should be decreased. So again, if W decreases with increasing width of BC, then what happened? Then how does beta value change? Beta increase or decrease? Go back to this equation for beta. If W decreases with increasing width of BC, decreases, then beta increases. Okay, so this is correct. So the meaning of increasing beta means collector current increases. Okay, so collector current increases, IC increases when as VBC increases. Okay, let's go back to the PMOS. BC, base, is corresponding to gate, and C corresponding to the drain. Okay, and this is working in active mode, so V sub EB should be very constant. So if we think about the emitter to collector voltage, which would be rewritten with a summation of V sub EB plus V sub BC. Okay, I mean that is VE minus VB, and that is equal to VB minus VC. So VB minus VB would be cancelled out, and in the end, VE minus VC, which is denoted as V sub EC. But in common emitter configuration, okay, in this case, V sub EB is constant. Okay, so that is constant. In other words, for a given value of V sub EB, depending on the VBC, your VEC would be determined, which is very identical and similar to the PMOSFET in saturation mode. Go back to the PMOS, gate, source, drain, and this is now in saturation mode. What about this voltage difference with source to drain? And here gate to source VSG should be constant for a given this value, and for a given source to drain value, your VGD value would also be constant. Okay, so that as VBC increases, in other words, your VEC increases, your W decreases so that beta increases, in other words, I sub C increases. So let's go back to this plot, IC versus VEC. Again, as VEC increases here, since this is a common emitter configuration, VEB is constant, so in the end, the VBC increases. Okay, so VBC increases. Then since VBC, I mean the base to collector junction increases, I mean this NP, PN junction is under reverse bias, so that this depletion layer would be expanded out, so that the quasi-neutral region in base would be shortened out. So W decreases. Then your I sub C, collector current or output current, in this common emitter configuration, this IC would be increases. Okay, so let me erase my note to clearly show you how to get this IC versus VEC, which is named as output characteristic. In common emitter configuration of VJT, you would like to draw the output characteristic plot. Then you should think what is the right value for x-axis and what is another right value for y-axis. I have talked about the output characteristics. Okay, then here output voltage, here output current. So in this common emitter configuration, the output current is matched to the I sub C collector current, and the output voltage means emitter to collector. So this voltage difference, because this emitter is common, okay, and your output node is collector. So with respect to the common node, which is emitter, how much voltage you got at the output node. So this VEC, no, plus minus. This voltage indicates your output voltage, okay? And since the VEC would be denoted as VEB plus VBC, okay? And previously I mentioned that in active mode operation, this VEB is constant, okay? So in rear, the output voltage is ineffective VBC. So as VBC increases, what would be happened? Base collector. So as this voltage difference between base and collector increases, what would be happened in your collector current, I sub C? If this BJT is in saturation mode, which is corresponding to the linear mode in MOSFET, your output current would be increases as your output voltage increases. So at the very initial stage, your BJT is working like resistor, but in the end, it's going to output the very saturated current. I mean that this beta DC would be constant. However, previously I mentioned that as V sub BC increases, this W decreases so that your output current increases, which is bad news, which is corresponding to the short channel effect in your MOSFET. Okay, so ideally your output current would be look like this curve. However, in rear, your current would be slightly increasing as your output voltage increases. This is bad news. So if your BJT is perfectly designed as an core transistor in analog circuit or analog amplifier, your output current, which is I sub C, collector current, should be saturated very well, whatever your output voltage is. So output current is very constant, whatever the output voltage is. Okay, that means output resistance is huge and infinity. But in rear, your output resistance should not be infinite. I mean the finite value you would get for your output resistance or output conductance. That means this slope should never be zero in rear BJT. So this short channel effect, maybe in your MOSFET design, ID versus 3D, you're very familiar with this curve. For a given input voltage, VGS, your output current, which is ID, drain to source current, should be very saturated. However, if your physical channel length is very short, then as output voltage increases, in this case VDS increases, drain current is also increasing. So you're gonna get this experimental data point in the end. So your MOSFET is not perfectly working as an independent current source in saturation mode, which is bad news when designing up your amplifier, MOSFET-based amplifier. Same thing would be happened in BJT as well. As your output voltage increases, your output current should be set and constant, ideally. However, in rear, your output current, which is I sub C, collector current is also slightly increasing. So this uh, slope should be removed, eradicated in the end. However, we cannot avoid, and we cannot avoid this base width modulation issue. Okay, so going back to this, the name of this slide, base width modulation. Modulation means something is changed, varied, right? And the base width indicates a W value, right? Quasi-neutral region of base, the physical width of the quasi-neutral base regime. So this W is very affected by the VBC, which is the ineffective output voltage. So depending on the output voltage of your BJT, your base width is significantly affected. Okay, so this is the main idea how to understand the base width modulation. Okay, and I guess yeah, on the left hand side, on the bottom side, let's see this plot more. Take a look at this figure. This is drawn the excess minority carrier, which is whole in anti-Brisson in base, right? Base as a function of x. I mean, in this direction. So the hole has been injected a lot from emitter side because this PN junction is now under forward bias because this BJT is working in active mode. So many holes would be injected into the N side. So here, this is corresponding to x of 0. Okay, so at thermal equilibrium in the base, how much hole has been created depending on the doping concentration in this anti-Brisson, or that is denoted as a base doping concentration, right? And how much emitter base voltage? I mean this voltage applied across this PN diode. Depending on this voltage difference between emitter and base, your initial excess hole concentration in the base at x of 0 would be determined. And this excess hole concentration would be originally should be exponentially decreasing. However, please review and refresh your memory with narrow base PN diode. If this quasi-neutral region width is very so narrow, then even narrower than the diffusion length of this minority carrier, which is a hole in this case in base regime, then the excess minority carrier concentration as a function of x can be written with a linear function, right? In narrow base width case. Then that's the reason why I have drawn the straight line here in between 0 to W. Okay. Well, definitely the base to collector voltage, this base to collector junction voltage across base collector junction would be set constant. Why is that? Because this is in active mode operation. Okay. So again, I guess we have already learned why this excess hole concentration in base is expressed with a first order linear function. Okay, please review that. All right. Now, since we have learned how to understand base width modulation, it's a good timing, good uh, right moment for us to come up with new ideas how to address, how to suppress base width modulation, which is bad news for designing BJT based amplifier. How to do that? Please take your own time how to suppress base width modulation. I'm going to give you maybe a few minutes to have your own time to come up with some your own idea how to suppress base width modulation. Go back to this cross-sectional view of this PMP-BJT. Suppose that you're the device engineer. Your job responsibility is to develop the new BJT, which is very robust and immune to the base width modulation. How to design your own BJT. Yeah, unfortunately, there is the three items how to reduce base width modulation, but please uh, forget about these three options for reducing base width modulation and think about your own design option, device design guideline. My question is, can you develop your own or can you present your own device design guideline from the perspective of reducing base width modulation of your BJT? How to do that? I'm going to give you maybe a few minutes. Please have your own time. I will come back soon, maybe 5 or 10 minutes. Please have your own idea. Okay, so I guess you have a sufficient amount of time to think about the ways to reduce phase width modulation. So let me explain those three different ways that I'm proposing. So number one is we can increase the physical base width. I mean the instead of WB, I'm talking about the W, quasi-neutral region of base W. So as long as W is very long enough, long, then we can forget about the base width modulation. But there is disadvantage of adopting this option. If your W is very wide, then your alpha sub T, what is this? Yeah, base transfer factor, right? The injected holes should go through the very long, wide base, which is bad news because the hole would be recombined with electrons in n-type base region. So this alpha sub T would be degraded. So in the end, your beta DC, common emitter DC current gain would be hurted a lot. So this is bad news. You would like to avoid base width modulation, but your DC gain would be hurted a lot. So there is a trade-off. Okay. And second way to reduce base width modulation is as follows. You can increase the base dopant concentration. In other words, your uh, acceptor concentration in base or N sub B. Then, uh, going back to this equation, I'm talking about this N sub B. If this N sub B is very high, then you may avoid this base width modulation. That sounds reasonable. However, the disadvantage of adopting this option is this. Your gamma emitter efficiency would be hurted a lot, degraded a lot, right? Because, injected holes from emitter would be recombined with electrons in base. But your electron concentration in base would be mainly determined by doping concentration in base. But since your N sub B has been increased, so that the injected holes from emitter would be more aggressively recombined with electrons in base. So that is bad news in terms of gamma or emitter efficiency. So in the end, since your gamma is degraded a lot, your beta DC is also hurted a lot. So that is not bad, very best options in terms of reducing base width modulation. So those two options sounds reasonable. However, its trade-off is bad. Let's go to the third way to reduce base width modulation. The answer is we can decrease, not increase, but decrease collector dopant concentration N sub C. So for given P and P BJT, emitter base collector. So your collector side doping concentration should be decreased. Okay, then your base width modulation would be alleviated a lot. What is the disadvantage of adopting this option? Yeah, the resistivity of your collector region would be increased. That means series resistance value. I mean, the original resistance value itself coming from the collector would be increases, which is bad news. However, this is the best way to reduce base width modulation. So the answer for this question, which of the above, option number 1, 2, 3, which one is the most acceptable action to address, to suppress base width modulation? The answer should be number 3. Then, I have just mentioned that the bad news of adopting option number 3 is this. Collector region resistivity increases so that the series resistance increases. But this disadvantage can be overcome. I mean, this issue can be uh, removed by what? We are going to learn the cross-sectional view of the modern BJT device. But here I'd like to draw the cross-sectional view of modern BJT device. So let's see. This is an N-type, N1 kind of N-wall, and that is P plus, and that is a tap cell. Okay, and here is a P, and below it, very heavily doped P plus region. So this is a collector base emitter. Okay, and this is matter contact. So MS contact, and here another MS contact. Why M plus is necessary to deliver electrical signal to this N-type base region? Yeah, think about the MS Schottky diode, the practical option for MS diode to achieve ohmic contact in between metal and semiconductor. If the semiconductor is super high doped, then the electron can move in both directions. So we're gonna implement the ohmic contact between MS. That is the main reason why we are going to use a heavily doped M plus regime uh, near the metal contact. Anyhow, emitter, base, collector. So if this p-type doping concentration has been decreased, then the bad news is our collector series resistance would be increased. How to remove or how to reduce the collector resistance rate? The answer can be found here. P plus, very heavily doped P plus regime has been attached, below the collector region. So I said below, so sub collector. So this P plus sub collector has been attached in parallel, again, in parallel to the collector region, this P type. So P plus, this kind of bilayer like PP plus design would be good enough to address this increased resistance. Okay, so this R series, increase the R series can be avoided. How? Yes, very heavily doped sub collector can be connected electrically in parallel to the p-type collector region. So this is the holistic view of the cross-sectional view of BJT. Not top view, but cross-sectional view. So emitter, base, collector, and sub-collector. And the bottom side is definitely silicon substrate. Okay, so for a given silicon substrate, you're gonna first fabricate P plus sub-collector, and beyond it, collector p-type region, and N kind of N-well. It looks like an N-well in CMOS fabrication, so N-type base and P plus emitter. And definitely this tap cell is necessary to have an ohmic contact between matter M1 or the contact. Okay, so we have learned phase width modulation, which is counterpart of the short channel effect in MOSFET. Now let's move on to the early voltage phase of A. Well, this early voltage has been also used in MOSFET to evaluate the output resistance. So similarly, in BJT, early voltage has been used and denoted as V sub A. So output resistance, RO, R naught here, is defined as how much output current, how much output voltage has been applied across BJT, and this is current, this is voltage. So on the left hand side, you're going to write down the resistance in the unit of ohm. So you should take an inverse value of this. Okay. All right. So these are out. So x-axis is the output voltage, y-axis output current, and in rear BJT, your output characteristic would be like that. the ideal output characteristic would be this, right? Yeah, the ideal output characteristic would be this. Very saturated IC should be demonstrated. However, because of the base width modulation, your output current is increasing as your output voltage increases. Well, definitely this VB plus VBC, this is a constant value, and that is varied. All right, so since ever increasing output current has been observed, so uh, we're gonna define this slope, okay? And this slope is corresponding to this output resistance, well, actually output conductance, because this is y-axis is current. So if this slope is 0, then the BJT should be very ideal. In other words, this output resistance would become infinite if your BJT is very ideal. So infinite means this slope is 0. That means if I'm drawing the tangent line, then you're gonna cross over the x-axis. So this point is defined as Ollie voltage. So Ollie means the person's name, okay? So Ollie voltage. Well, if your BJT is very ideal, and in other words, its slope is 0, then VA would be infinite. So since you'd like to make your BJT very ideal, uh, only voltage VA should be very large. So a large VA is very desirable. So larger VA means, right here, the larger VA means your output voltage increase very high. So larger output resistance is very desirable. So when it comes to the analog amplifier, the output resistance, ideally infinite. So that is the main reason why your only voltage should be infinite. The higher only voltage is, the better it is. Okay, so we have went over the only voltage definition and how to extract out the only voltage in output characteristic plot. And now let's move on to the derivational formula equation for only voltage VA. How to write down the equation for VA? The answer can be found at the last line of this slide. VA can be written with this three term: base stopping concentration, quasi-neutral regime or quasi-neutral base region width, and this guy, junction capacitance in base collector. Okay, so Q is unit charge. So those are three factors will determine your only voltage. Okay, so then you may come up with your own device design guideline, how to make only voltage infinite. The answer can be found here. You may increase the base stopping concentration, or you may widen out your base width, but that is very bad news in terms of beta DC, right? Your amplification factor would be hurted a lot. So the answer can be found here: junction capacitance in between base and collector. So by the way, in this slide, let's derive the formula for only voltage step by step. So output conductance. Previously, I mentioned that output resistance, okay? But now I said output conductance, G naught, which is our 1 over RO, output resistance. And the G naught, output conductance, can be defined as output current divided by output voltage. And that is defined as only voltage. Go back to the last slide here. RO is defined as only voltage divided by output current. Okay, and G naught, output conductance, is defined as the output current divided by only voltage. Remember it and take a look at here. Okay, G naught IC over VA. So we can rewrite the only voltage as a function of output conductance and output current. Now, the output voltage VEC, the voltage difference between emitter and collector, can be rewritten as a two voltage component, EB voltage and BC voltage, so that your output conductance G naught is defined as this, and instead of VEC, instead of this guy, because at in active mode, go back to here, yeah, the BJT is now working in active mode. Your EB, emitter base junction voltage, VEB, voltage difference between emitter and base would be constant, right? So this guy is constant. So plug in your two voltage value here. And since VEB is constant, you can ignore it when it comes to take derivative of it, right? So VBC is left behind. So for fixed VEB, again, you can replace VEC with VBC. Okay, now G naught output conductance can be written as DIC dVBC, DIC dVBC. But using chain rule in calculus, let's use the derivation of base width. I mean this. Okay. All right. So now let's look for the more detailed equation for this term and the second term. But before moving forward, this W is very dependent of VBC, base collector voltage difference in this PN diode, right? So if VBC increases, W increases or decreases. BC means, this guy, right? So VCB decreases, W increases or decreases. So CB means PN. Okay, so this PN junction, the voltage difference in this PN junction decreases. That means W decreases, right? Under forward bias, the depletion layer width decreases. So that this depletion layer width would become smaller. In other words, this W increases. So again, VCB with a smaller VCB, your depletion layer width decreases. In other words, the quasi-neutral base width increases here in the W. Okay, so don't be confused with the depletion layer width W that I have just explained. Anyhow, this NP diode, if this PN diode, okay, this PN diode, the VCB decreases. I mean, the less forward bias increase, less forward bias is applied, then your depletion layer width decreases. In other words, the quasi-neutral region in this N side, which is base, increases. Okay, so W increases. The quasi-neutral region of base. But the meaning of decreased VCB is corresponding to the increased VBC, right? Not VCB, okay? So as VBC increases, your W increases, which means X and C, the depletion layer width, X and C decreases. So this trend is opposite to each other. So that's the reason why I have put the minus sign here, okay? All right. So now, let me take a look at here. We would like to know the full equation for output conductance G naught. So we would like to look for the detailed equation for this guy and that guy. Okay. So the first guy here, DIC should be written with a full equation. How to get? In the previous study, we have derived the full equation for collector current ICP plus ICN. So we have developed each current component for collector current, and we end up with this long equation. And since this BJT is working in active mode, so that the second term can be ignored. Why is that? Your W is much shorter than the minority carrier diffusion length, so this second term can be ignored. If you cannot remember what happened in this process, please go back to my previous movie clip and review what happened to and how to get the full equation for collector current. And then, anyhow, let's ignore this term. Then you're gonna end up with this equation. Very simple. Okay, even this hypersign can become W over LB if W is much smaller than L sub B. Okay, then you're gonna simplify the equation shown in first line as follows. Okay, all right, now it's time to take a first derivative with respect to W. So you can see that W is here. Okay, so it's very simple one, something times 1 over W, and take derivative with respect to W. Please do that. Very simple. That is minus 1. So if we take a derivative with respect to W, that is, minus 1 times W minus square times something, right? So that process has been done and shown in here, okay? And let me erase my note and take a look at here. Just W times W. And take a look at this guy. That is exactly same one as IC, right? So single W has been left behind and the other things can be rewritten as a single term, which is IC. Okay, so the conclusion is DIC dW is equal to IC over W, and don't forget the minus sign. Okay, so we done. DIC dW is equal to minus IC over W. So plug in that value into here. Okay, now it's time for us to move forward to get the full equation for this second term. So here you can see the second term, right? So how to get this guy? To know this guy, since this is a depletion layer width, and that is voltage, and depletion layer width can be written with charge, total charge in the depletion layer. So since this is a PN diode, right? I mean this PN diode. So in this PN diode, junction capacitance or depletion CDEP, depletion capacitance. This C indicates a collector junction. Okay, so collector junction means, this is emitter base collector. So this is a base collector junction. I'm talking about this junction. So in collector junction, you can derive the equation for junction capacitance or depletion capacitance. So the definition of a capacitance is this: how much, depending on the voltage difference across this junction, collector junction, how much charge can be attracted. So in the depletion layer of the collector junction, how much charge can be attracted for given voltage difference in between base and collector region. So this is very simple definition, and now let's write down the equation for this QDAP, depletion layer charge. So in the depletion layer, which would be the main origin of being charged? Yes, ionized dopant atoms. So in base, there is tons of acceptors which is positively ionized. So that is the reason why I have a plus Q times doping concentration in base. But that Q times N sub B indicates Coulomb per cubic centimeter. Okay, and now since the PNP BJT has been analyzed in along one dimension, x dimension only, so we should multiply the depletion layer width, since we are looking for how much charge has been stored and attracted in this depletion layer in collector side. Okay, so X and C. Again, what was the X and C? Yeah, X and C is the depletion layer width of the collector junction side. Okay, so take a look at here. All right. Okay, so we almost done. Herein, Q N sub B is constant with respect to the voltage difference between base and collector. So Q is out and B out. Okay, and the leftover is this. Okay, so C junction capacitance in collector junction can be expressed with these two terms. Okay, now take a look at this guy. That is the guy that we are looking for. This, right? So now let's rearrange all the terms with respect to this guy. Okay, then you're gonna end up with this C junction capacitance divided by Q times N sub B. Definitely this Q is 1.6 times 10 to the minus 19 Coulomb. N sub B is acceptor concentration in base, right? Okay, so this is number 2, and plug in into here. Okay, then let's go back to the early voltage. Output current divided by output conductance, and the IC is same, and the output conductance is rewritten as a multiplication of two terms. And the first term is, let me erase it, DIC here can be found here, so plug in here, so you will see that minus IC over W. And the second term here can be found here, right? And the second term can be rewritten as a junction cap over Q times NB. So plug in here, don't forget this minus sign, okay? So take a look at here, junction cap divided by Q times NB. So now this minus minus cancels out, and IC cancelled out, and W, Q, and B divided by junction cap. All right, we done. Early voltage VA is defined as unit charge, base doping concentration, quasi-neutral base width divided by what? Junction capacitance of the collector junction. So this is the very simple equation for early voltage. In ideal BJT, this early voltage should be infinite. For that purpose, base doping concentration should be as high as possible, and the quasi-neutral base width should be as long as possible. However, this increased and be widened width would degrade your beta DC value, which is bad news when you are using this BJT for your amplifier. So the answer can be found here. Junction capacitance should be well checked and managed to get very high value of early voltage. Okay, so that is uh, the last comment of this second lecture note of BJT. So in the upcoming week, I'm going to wrap up the lecture note for BJT. So BJT lecture note number 3 will be explained in the upcoming movie clip. So herein, I guess you should preview what we are going to learn. Let me briefly tell you. So I guess since our lecture is about wrapping up, within a few weeks. So I guess it's a good time for you to review what we have learned as well as to preview what we are going to learn. So the corresponding chapter of the textbook, BRS book, is 11.2 and 11.3. So please take your own time to read all the sentences in chapter 11.2 and 3 to understand some non-ideal effects in BJT. So one of the non-ideal effect is breakdown mechanisms, okay? And Gummel plot and Gummel numbers would be used in determining the non-ideal effects and in explaining your BJT device is good or bad. So Gummel plot, Gummel numbers are a good indicator and good design parameters of your BJT. Afterwards, we are going to learn the cross-sectional view and bird's eye view of modern BJT device structure. So this is the you know it looks much more complicated compared against the single gate planar bulk MOSFET. So you may get this kind of insight. Aha, BJT needs much more area in silicon substrate. Planar bulk MOSFET needs very tiny and relatively smaller area in integrating or inputting a single MOSFET onto the silicon substrate. This is the main reason why MOSFET is mainstream other than BJT. A few decades ago, maybe 5 or 6 decades ago, BJT is way better option in designing IC chip because it's working perfectly, almost like an ideal transistor. However, since planar bulk MOSFET or CMOS FET technology can give us a tremendous amount of advantage in terms of power consumption. So people in industry has adopted planar bulk MOSFET because it is good to suppress power consumption. And even on top of that, the layout area, the chip area for MOSFET is much smaller than the chip area or layout area of single BJT onto the silicon substrate. So in the end, BJT has become the second tier one in designing analog circuit amplifier and others. So all the digital chip, say GPU, CPU, are usually and mainly using MOSFET only. BJT is out. However, still, the modern BJT is necessary when designing very super or high amplifier. So for analog circuit applications, still there is a huge room left for BJT. Okay, so please remember it and have your own time to preview breakdown mechanisms. Let me briefly go over here in IC versus free EC plot. You know, here output current characteristic, right? And in your MOSFET, the output characteristic would be this. But in the end, it's going to be show us the exponentially increasing output current. So this is understood as a breakdown in MOSFET. So same breakdown can be observed in BJT as well. And this Pontius Rule. So Pontius Rule means the quasi-neutral base region has been gone away. I mean, there is no more quasi-neutral base region left because of this collector base junction voltage and emitter base junction voltage. Okay, so once the quasi-neutral base regime has gone away, then what would be happened? This is non-ideal effect. So that mechanism and this physical event is named as Pontius Rule. So we're gonna learn it. What about the avalanche multiplication? So you remember the impact ionization stuff. So those kind of things would be happened in the base collector junction when very high reverse bias has been applied across base and collector junction. So avalanche multiplication would be happened. And some other non-ideal effects will be followed up, high-level injection, series resistance, those kind of jargon professional words has been already used in explaining the non-ideal events happened in PN diode. So, same word would be used in this PJT as well. Afterwards, we're gonna learn the definition of Gummel plot and as well, followed by Gummel numbers. So these Gummel numbers and Gummel plots are significant one when it explains your BJT is good or bad. Okay, so we're gonna learn it later. And now the last one is modern MPN or PM. Herein I have brought the cross-section review of modern NPN BJT structure. However, you may draw your own cross-section review for modern and PNP BJT structure as well. So here main features of this modern NPN BJT structure will be explained in the upcoming week. Okay, and moreover is a polysilicon emitter. Instead of silicon, what if we are using polysilicon only in emitter region? What would be happen? Maybe diffusivity, diffusion length, that kind of stuff would be affected because this is a polysilicon, not crystal silicon. Okay, and heterojunction bipolar transistor or HBT would be explained at the very last moment of the upcoming lecture. And some example problem and others based transition time, charge control model. Well, we have already used it in analyzing PN diode. So we're gonna reuse it for BJT analysis. Okay, so please have your own time to preview the last lecture note, okay, because we are short of time. So I would like to ask you to briefly go over and preview the last lecture note for BJT. So see you in the next week and have your own time for reviewing what you have learned this week. See you in the next week. Bye bye.